All right, 3.7 implicit differentiation, part A. Um, implicit differentiation has to do with deriving when you have x's and y's in the function. So let me explain. Implicit. That is something or an equation or a function that would look like this. X times y equals 1. See how they're both on the same side of the equal sign? What we're used to, or what we've been doing, is something that would look like this. Y equals 1 over x. That's explicit. It's explicitly solved for y, and all of the stuff that we derive is the x part, right? All the x parts. The implicit form can be made to look like the explicit form. For example, if I divide this by x and divide the other side by x, that goes away, and I have y equals 1 over x. And that's how I got that. Now that's the normal stuff that we're used to deriving. And then to derive, you'd be like, okay, dy dx, that's the derivative of 1 over x. You know, you can rewrite this as x to the negative 1 power. You would bring the negative 1 to the front, and then x, and then subtract another exponent. Okay, so that's what we're used to. Today's lesson is deriving implicit equations, or equations in implicit form, where it's really hard to get the y by itself. We can't solve for y as easily as I did here, right? So you have to do it another way, and it's implicit differentiation. Now there are 4 steps to implicit differentiation. Step 1, you're going to differentiate both sides of the equation with respect to x. We always derive with respect to x. And that's the tricky part because of the y. And I'll explain as I'm doing it. Step 2, collect all the terms involving dy dx on the left side of the equation and move all the other terms to the right side of the equation. Okay, step 3, you're going to factor the dy dx's out of the left side of the equation. And then depending on what the equation looks like, step 4, you're going to solve for dy dx. Usually involves division somehow, sometimes, most of the time. Okay. So, example 1. Same old, same old. This is regular stuff. So I'm deriving x cubed for a. So that is 3x squared. Well, I need to explain. Implicit differentiation is going to work with the same rules. It's just that whenever there's a y, there's going to be like an additional step. So b, if you look over to b is a very similar function. It's y cubed instead of x cubed. But I'm still deriving with respect to x. Now y is not x. So you're going to make pretend that it is. You're going to use all the same rules, all the derivative rules that we've learned so far to derive for y. So this is going to be 3y squared. Okay, very similar to part A. Let's see. So, right? 3x squared, 3y squared. But because this is implicit differentiation and that is not x, I have to make up for that. I have to compensate for that somehow. So it's like a mini chain rule. 3y squared becomes 3y squared times dy dx. And every single time that I take the derivative of y, I have to write dy dx because that is the derivative of y. Since the first time that we started doing derivatives, whenever you derived an equation y equals, one of the options to use was dy dx, right? When you did the derivative, okay, same thing, kind of. I'm just going to multiply by dy dx. And there's the chain rule aspect of it. I took the derivative of the outside, which was y cubed, and then I multiplied it by the derivative of the inside, which we're considering to be y. Okay, C. I'm deriving again with respect to x, right? That little x tells me that's what I'm respecting here. So x plus 3y becomes, let's see, the derivative of x is 1, and then the derivative of 3y would just be 3. But because this is y and not x, dy dx. And that's the derivative of that. I'm not solving for dy dx just yet. I'm just doing this. Okay, D, I have x times y squared. So this is a product rule. Okay, this is u times v. So I'm still going to do my product rule like normal. But it's just implicit differentiation because of that y. Okay, so u would be x. Let me do it down here. So u is x times v prime times the derivative of y squared. The derivative of y squared is 2y, but then dy dx. Plus v, which was just y squared. Now I'm not taking the derivative of v, right? That's just v. So I don't need the dy dx. The dy dx is only when you take the derivative of y. Okay, so v is y squared times u prime, which is the derivative of x, which is a 1 that I don't need to write, but I'll write it in anyway. Okay, and that'll be that. Could probably write it a little prettier, but I'm just trying to ease into this. All right, next. All right, example 2, find dy dx given that y cubed plus y squared minus 5y minus x squared equals negative 4. Okay, so this is an implicit differentiation. I'm going to do every single derivative, but remembering that every time I take the derivative of y, I have to tack on that dy dx. So using your guidelines on the above part of your notes, differentiate both sides with respect to x. So 3 times y squared, that's the derivative of that, but oh yeah, dy dx. Okay, plus 2y dy dx minus 5, because that's the derivative of 5y, but dy dx, minus 2x equals, and the derivative of negative 4 is 0. So step 1, differentiate. Step 2, collect all terms involving dy dx on one side. We're going to say the left. So that means that I need to leave certain things. For example, see the dy dx here, and the dy dx here, and the dy dx here. So all of these are going to stay on this side, and I'm going to get rid of any terms that do not have or do not involve dy dx. So minus 2x becomes plus 2x, right? I want to move it to the other side, plus 2x. So now I have, again, 3y squared dy dx. And I'm not going to be writing this over every single time. I'm just doing it this first time, because you should be able to move around things without totally spacing out, or spazzing out, rather. Now, the purpose of me getting rid of the only term without the dy dx was because now I have the opportunity to factor out these dy dx's. They're going to get factored out. And that is step 3. Factor dy dx out of the left side. Okay, so now I have 1 dy dx all by itself in the front. And in here, I'm going to have whatever I had left over once I got rid of the dy dx's, then equals 2x. So let's see, without the dy dx, I have 3y squared plus 2y minus 5. Okay, so my goal is really to get this by itself, because my derivative will be dy dx equals a bunch of stuff. So in order to get the dy dx by itself, just using regular math rules, right? These are being multiplied. So to get rid of the stuff in the parentheses, I'm going to divide all of it. 3y squared plus 2y minus 5. So I'm dividing it away. But of course, whatever I do to one side, I must do to the other. So 3y squared plus 2y minus 5. This gets canceled out. And now I have dy dx all by itself equals 2x over 3y squared plus 2y minus 5. And that's it. That's my derivative. Okay, here are two equations. I want you to try to solve them yourself. So now would be a good time to pause and try to see if you could do it. And then watch the video as I do it. Okay, so for part A, 2x squared plus y squared equals 9. So this becomes 2x. That's the derivative of x squared plus 2y. But I took the derivative of y, so I have to multiply by dy dx equals the derivative of 9 is 0. So here I want to get everything that has dy dx in it. I want to leave it alone, and I want to move everything else. So the 2x doesn't have a dy dx, so I'm going to move that over by subtracting it. And then now I have 2y dy dx equals negative 2x. I want to isolate the dy dx, and the easiest way to do that is just to divide this by 2y. It'll cancel out that 2y on top there, and then I have to do it to the other side as well. Right? Simple algebra rules. So now the dy dx, it's by itself. And then I have basically negative x over y because the 2's cancel out. And there's my answer for that. All right, for B. So 3x squared minus, that x and that y, they're being multiplied. That's a product rule. So let me go ahead and do that in like brackets so you know that that's what I'm working on still. So u and v, right? So let's see. U times v prime. Okay, v prime, the derivative of y will be 1, but then I can't forget the dy dx. Plus v, which is y, times u prime, which is just 1. Now notice, you could join the negative outside here. The negative xy, you could have made it negative x. I just left it alone. I can do something with it later. Then plus, and then that's 2y dy dx, and then equals, and the derivative of that is 0. So let me write this out with the negative now. So negative x dy dx minus y plus 2y dy dx. Okay, now next step is to get all the dy dx's alone and move everything else away. So this would get moved to 3x squared, and this would get moved because neither one of them have a dy dx attached to them. And then I would move them over to the other side, right? I'm a little limited on space. Bear with me. Okay, so bye-bye, bye-bye. So I have negative x dy dx plus 2y dy dx. And that equals the stuff that I moved over. So y minus 3x squared. Okay, isolate the dy dx's. So I'm going to factor them out. I'm going to factor this out, and I'm going to factor that out. Right? So I have 1 dy dx out in the front, and in the parentheses I have negative x plus 2y, and that should equal the y minus 3x squared. I want to still trying to isolate the dy dx, so now I'm going to divide. I'm going to divide all of this by the stuff that's in the parentheses, and then I'm going to do the same to the other side. So this will cancel out and leave the dy dx by itself. And then on the other side, I'll just have y minus 3x squared over negative x plus 2y. Or you can write 2y minus x if you don't want to put the negative in the front. That's okay. That's perfectly fine. And there's my answer. All right, deriving trig functions implicitly. So example 3 says find dy dx for sine of y equals x. So I'm going to do the derivatives like normal. The derivative of sine is cosine. It's just that instead of x, it's a y. So because of that, dy dx. And then that equals the derivative of x, which is just a 1. I'm still trying to do the exact same things as before. I need the dy dx by itself, so everything else is going to have to move over. This one doesn't require so much work because the cosine y is being multiplied with the dy dx, so all I have to do is divide by cosine y. Both sides, of course. So then I end up with dy dx equals 1 over cosine y. That's basically my answer, except for the fact that I should know a few trig identities, right? And you should know that cosine, and I'll use x, is equal to 1 over secant x, and secant x is equal to 1 over cosine x. Right? So this is actually, I could rewrite it as secant y. Sorry, I almost wrote x. So dy dx is secant y. Example 4. Find dy dx for 4 cosine x sine y equals 1. So this is a product rule because these two functions are being multiplied. So what I want to do is I'm going to call all of this, I'm going to call it u, and I'm going to call all of this v. It wouldn't hurt to list everything out. U is 4 cosine x. U prime is going to be the derivative of that, which is 4 times negative sine x, right? V is sine of y. So v prime will be the derivative of that, which is cosine y, but then dy dx. Okay, that's similar to the chain rule because of the du part. Okay, so I got my pieces. I'm going to go ahead and derive this. Let's see. So u times v prime plus v times u prime, which is negative 4 sine x, equals the derivative of 1 is 0. So my objective here is still basically the same. I have to get the dy dx's all together by themselves. And I see that there's only 1. So that's convenient. So what I'm going to do is I'm going to move what isn't attached to a dy dx. But before I do that, I would like to take care of this negative right here. That negative 4 sine x and sine y being multiplied is just basically minus sine y, or you know what, I'll do the sine x. I forgot about the 4. Minus 4 sine x sine y. Let's go ahead and write it like that. And then this is still just 4 cosine x cosine y dy dx. Okay, so get rid of all of this because it does not have a sign or dx, dy dx attached to it. So I'm going to add it, and I'm going to add it to the other side too. Plus 4. I just got no space. Okay. So I have 4 cosine x cosine y dy dx equals 4 sine x sine y. Okay. I need the dy dx to be by itself, so I'm going to divide this side by the cosine x 4 cosine x cosine y. And those are going to cancel out, but then I got to do it to the other side too. 4 cosine x cosine y. All right. So now what I have is dy dx, of course, because that's what my goal was, by itself, equals. Now, the 4's, they cancel each other out. 4 divided by 4 is 1. The sine x over cosine x, though. See these right here? Sine over cosine is tangent. And then same goes for these. Sine over cosine is tangent. The only difference is that one is for x and one is for y. So sine over cosine is going to become tangent x. And then sine over cosine, but with the y's, it's going to be tangent y. And there's my answer. All right, tangent and normal to the curve. The word normal means perpendicular. You may also encounter the word orthogonal. Okay? All right. Example 5. Determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at the point square root of 2, negative 1 over square root of 2. Okay, so the slope. In order to find the slope, you have to derive. Okay? The derivative. So I'm going to derive this function. And then I'm going to plug in my x's and y's to find the derivative, the slope. Okay, so implicitly, this is 2x plus 2 times 4 is 8, and then there's a y left over there. But because I derive with respect to x, and this is not x, dy dx equals, and then 0. So there's my derivative. So I'm going to go ahead, I'm going to get the dy dx by itself. And I'm going to do that by subtracting 2x to the other side. I'm not going to write it down. So 8y dy dx equals negative 2x. So now I'm trying to isolate the dy dx. So that means that 8y has to be divided away. So I'm going to divide it from both sides. And I'm going to end up with dy dx on this side equals negative 2x divided by 8y. And of course that simplifies, right, to negative x over 4y. So this here is my slope. All I need to do is plug in my points to figure out what the actual numerical value of the slope is. So let's see. dy dx is equal to negative x, so negative square root of 2 over 4 times y, so 4 times negative 1 over the square root of 2. And then I have, okay, so 4 over the negative 4 over the square root of 2. Now the negatives, they basically become positive, right? So I don't got to worry about that anymore. But this is a fraction inside a fraction, no bueno, can't do. So what we do is, since we're dividing fractions, the way to divide fractions is to keep the top number in this instance, or the first number, the top number the same. we're going to change to multiplication, and then the second number, or the bottom number, is going to be flipped over. We're going to multiply by the reciprocal. This should all be familiar, right? So, square root of 2 times, and instead of 4 over the square root of 2, it's going to be the square root of 2 over 4. Square root of 2 times the square root of 2 is 2, and then the 4 is just 4, and then 1/2. There's my slope. dy dx is 1/2. All right, example 6. Find the lines that are tangent and normal to the curve. So tangent lines have the same slope. So whatever slope I end up with, that's what I'm going to use to write the equation. Normal lines are perpendicular, so the slope is the opposite reciprocal. Okay, so first I'm going to find the slope. In order to find the slope, I have to derive. So 2y dy dx minus 2 minus 4, and then dy dx. The 1 is 0, and the 0 is still 0. There's my slope, or my equation anyway, that gets me the slope. I need to isolate the dy dx's, and I need to move anything not attached to a dy dx. So let's see. This is going to stay here. dy 2 dy dx. The negative 2, that baby's moving over as a positive 2 to the other side. So minus 4 dy dx. And like I just said, that negative 2 came to the other side as positive, right? Because I added 2 to both sides. Okay, I'm going to factor out the dy dx's. So I have one big fat dy dx out in front here. And then 2y minus 4. And that equals 2. I need to get the dy dx by itself. The only way to do that right now is to divide. So I'm going to divide 2y minus 4 from both sides. I'm going to end up with dy dx equals 2 over 2y minus 4. So basically, that is the equation that will get me my slope. I need to plug in my points. My points were negative 2, 1. Okay, plug in negative 2, 1. Let me look at this equation. I have 2 divided by 2y minus 4. There aren't any x's. So the only number I have to actually plug in is the y value. So I have 2 over 2 times 1 minus 4. So 2 over negative 2, which is negative 1. There's my slope. Okay? All right. So there's my slope. Now that I have my slope, I'm going to write my equations. So for the tangent, I'm going to use y minus y1. y1 is 1, right? This is going to be my x1. This is going to be my y1. Equals slope, which is negative 1, times x minus my x1, which happens to be negative 2, so that becomes positive. And then simplify a little, right? And then move the 1 over by adding it. And there's my equation for the tangent. All right, for the normal, I'm going to do the same thing, basically. But for normals, the slope is the opposite reciprocal. Okay, so if my slope was originally negative 1, to do the opposite reciprocal, it's going to be positive 1. Okay, so for my normal, I'm going to do y minus y1. You can't see it, right? y1, which is 1, equals positive 1 times x minus my x1, which was already negative, so that becomes a plus. So y minus 1, simplify a little. And then add 1 to both sides. And there you go. There are my equations. Do your homework, please. Thank you.